that you learn more about bones is actually by touching the bones and looking at the bones in a 3D, like on your hands, right? That's the best way I think that you have to learn more about the shape of the bones. So here we are going to focus a lot on the microscopic and functional aspects of the bones. So the PowerPoint that I put up, right, the PDF file that I put up, I know it's a lot, but we're going to really focus on the aspects that you absolutely have to understand, right? And I hope that it is in a way and in a sequence that makes sense. And again, in this chapter, there are several explanations that at first didn't quite make a lot of sense. And then, again, I started to look at different sources and different explanations, and still I'm not quite happy with them. So, well, let's see what happens. Yeah, the PowerPoint I have now, it's about the same as the one you have, because I really wanted to improve a lot before coming to class, but then I just spent 2 hours in a Zoom talk with this developer. So let's see what happens. If you have questions along the way, if something is not making a lot of sense, ask. Okay, this is supposed to be a semi-interactive kind of class. Oh, and something else. If we don't get to cover all the topics that I think are absolutely necessary in this chapter, I am going to prepare videos and I'm going to put them up and add them in the module so you can watch them just in a sort of a partially inverted classroom style. Okay, so, and also we don't fall too far behind in the subjects that we want to cover. Question: the growth of cartilage from within the cartilage is termed what? Yeah, that was interstitial growth. We still have people who put a lot of other stuff, right? So that was your first point. Next question. Terms long, short, flat, and irregular are used to classify bones based on their what? Yeah, exactly, but you didn't get the points, remember? And that is classification based on shape. And here is your next freebie. A group of concentric rings of bone matrix composing the functional unit of the long bones. So this is a hard bone, right? Dense bone. Is called what? The osteon. Concentric rings. Remember, your osteon is made of little concentric rings. Yeah, okay. So let's see. I think this is the last of it. All right, so now this part of osseous tissue of the lecture is really with a lot of concepts that are a bit difficult to understand at first and then to digest and then to get used to it, right? So let's pay attention here, because by the time we get to the next chapter, that's when the things get to be, I would say, a bit too much memorization, right? So for chapter 7, mainly I'm going to put slides of bones that I'll ask here, because you're still going to have a lot of bones and a lot of memorization in your lab, right? So I don't want to really be a lot very redundant with the things here in the class. So well, you'll see when we get there. So here, for this part of the class, we had stopped here last time, right? We had mentioned that you have interstitial lamella, right? Here is your osteon, right? So remember, we had the osteon as the unit of the dense bone, and we had mentioned that the osteon is made of this central canal, right? And that's your haversian canal. And besides the lamella that are making part of this osteon, you also have this interstitial lamella that is between, like found between these osteons, not part of the osteon itself, okay? And then, as you see the description here, some are going to fill the gap between these osteons. And then you have this circumferential lamella, and those are found really around the whole bone and just under that membrane, that very strong membrane of the bone that is called the periosteum, right? So that circumferential lamella is really going to form those outer circles of there's like almost like encasing the bone. Okay. Now, these circumferential lamella are kind of important for the function of the bone because they do help the bone to resist fracture when the bone gets twisted. Right? And then you're going to ask, when is it that the bone gets twisted? Well, if you just average person and you're just walking and not doing anything really strange with your bones, then you don't really have that much of a problem. But if it happens that you are an athlete, especially like in gymnastics or I don't know, baseball or anything that you have to turn very quickly, then your bones are really under a lot of twisting pressure, and that if you don't have that nice composition of those structures, specifically of this circumferential lamella, then your bone can kind of get a fracture due to the twisting. Right? So know where those are located. And when you look at this compact bone, right, this dense compact bone, we had mentioned that not only you have the central haversian canal, right, but you also have other forms of communications and other canals. And one important one to remember is this Volkmann's canal. And that communicates different osteons, like the haversian canals, communicates to each other. So haversian canals, they run parallel to the axis of the bone, right? This is like parallel to the axis of the bone. Those are the haversian canals. Now, those Volkmann canals, they run at 90 degrees, right? Perpendicular to the axis of the bone. And so those are connecting the haversian canals to each other. Okay. And then here you also see this structure of canaliculi that they are helping the osteocytes, right? They are sitting inside of this lacuna, right? So the osteocytes communicate with each other by stretching their hands or their tentacles to these canaliculi. So they communicate to each other via these little openings. Okay, so canaliculi between lacuna. So here looking at the spongy bone, right? So anatomy here is a spongy bone. Now it seems like it's just a mess of spongy stuff that is not soft. Okay, it just looks like a sponge, but it's not really soft like a sponge. Okay, so it seems like it's not really organized, but actually it is very organized. And is meant to be in this type of organization so that it can withstand pressure from all the sides. Now, when you look back into your dense long bone, you see that mainly it's meant to withstand pressure from top and from the bottom. Right? So you have like those structures, like osteons, structures are like little straws. They are meant to withstand pressures that are perpendicular to the axis of those osteons. Now, this type of spongy bone is able of sustaining pressures from any angle. Okay, so basically, when you look at the structure, for example, of a long bone, you see that the top and the bottom of the long bone, how do you call those structures at the top and the bottom? It starts with the E, epiphysis, right? You see the top and the bottom, they are really made mainly of these spongy bones, because when you walk or jump or run, the pressure has to be absorbed by these spongy structures and then transferred to the long bone and then transferred again to the other epiphysis, to the distal epiphysis, right? So you have the proximal and the distal. You remember those terms, right? Proximal and distal, that's very basic. You should remember them. Okay. So what makes these structures here, okay, this structure here, this is called trabecula. Okay, so this is like stuff that's holding everything together. Okay, at first I thought trabecula were just the names of the holes because it said, oh, little beams. In my head, with my Portuguese background, I read beans. So beans, like black beans, you know, like bean soup. In my head, it was like the little holes, you know. And then I just they were talking about beams with the M, right? So it's not the beans, it's not the holes, it's the structure itself. So don't get that confused. If you come from a different country, these are the beams, okay, not the beans. You got it? All right, the structure itself, not the lack of structure. All right, cool. So these beams here that really hold this whole thing together and are able to withstand the pressures. Okay, so there are no osteons over there, right? There are some structures that might resemble osteons, but they're not osteons. Okay. Now you also see osteocytes sitting in their little cage, in their little lacuna, right? You also see some lamella. You also see osteocytes communicating by canaliculi, right? Extensions that go through the canaliculi. But the unit, the functional unit here, there's no real functional unit that is the osteon. There's no osteon there. Okay. So remember, because that's one important difference between the two types of bones. Now, with the osteon, we saw that you had the central canal, right, the haversian canal, and this is how you had the nutrients that would come through the blood vessels. They'll go through the central canal. Besides blood vessels, what is it that you have in the central canal, in the haversian canal? Nerves and something else. And I'm not sure if I mentioned last time or not. Blood vessels and well, arteries and veins are part of the blood vessels, so we're missing one. Starts with the L. Lymphatic vessels, yes, right? Because you have to have the circulation, the close circulation between the arteries and the veins, but then you also need the lymphatic system to absorb whatever leaks out of that junction between the veins and the arteries, right? So you have arteries, veins, nerves, and lymphatic vessels, all going through that little canal. Now, when you look at this holy mess here, pun intended, right? So you don't see that. You don't see the osteon, you don't see those canals. And how is it that the osteocytes sitting their little, you know, lamella, I always get those confused. Which one is the osteocyte sitting on? Lacuna, right? Okay, don't get them confused. I always get them confused. So we don't have that here. So how is it that the osteons here are going to get their nutrients? You're just reading that, right? Yeah, but what does that mean? The endosteum, what is the endosteum? The membrane, right? Remember, the membrane is full of capillaries. It's very vascular. Endosteum and periosteum around the bone is very much full of blood vessels. Now here, those osteocytes are really going to be nourished by those capillaries that are very much stuck to the bone by that present in that membrane. Okay, so they don't really need those central canals, the structures that we've seen before, because here you have plenty of area, of surface area, for those osteocytes to get their nourishment based on those on the attachment here of the endosteum that has all of these blood vessels. Okay, so that's also another major difference in the structure of these bones. Okay. So here we go with the beans, or the beans. No, don't spill the beans. Those are beans. Okay, so these trabecula, those are what we call those little beans. again, when you look at the bones, you probably have seen this in the lab already, right? You're going to see that the bones, you're not going to find only one form of bones when you look at a bone. You're going to find spongy bone, and you're going to find compact bone in the same bone. So the compact bone tends to be on the outside, right? And of course, it's a lot denser than the spongy bone, and is also a lot heavier than the spongy bone. Okay, a reason why spongy bone has a lot of holes is because it has to be light. It has to be efficient at absorbing shock, and it has to be light. It cannot be heavy. Now, this compact bone here it is a lot heavier. So when you look at the whole architecture of the bone, you're going to find mainly compact bone outside and then spongy bone like on the inside of the bone. Okay. And even when you look here at the diaphysis, right, of the bone, you're going to find some spongy bone that is internal in reference to the compact bone that is on the outside, just under the periosteum. Okay. So now when you look at flat bones, they also have a layer of spongy bone in the middle and is basically sandwiched by compact bone on the outsides. Okay, so spongy bone in the middle and compact bone on the outside. Okay. So we've seen that bones are made of both organic and inorganic stuff. Okay, so question is, what are the organic components of the bone? So in the organic components pool, we're going to put all the cells. Okay, so all cells are part of organic stuff. And also this osteoid. Now, anybody remember what's the osteoid? Matrix, organic stuff of the matrix, just before it gets calcified. Okay, so this is secreted by the cells, mainly by the osteoblasts, and then the osteocytes maintain the osteoid composition, right? Now, osteoid is mainly made of collagen fibers. Okay, so this is your osteoid thing, but it is before it gets calcified. So it's missing the inorganic stuff, okay? Mainly hydroxyapatite that is going to calcify it and make it really solid. Okay. Okay. You have, I'm sure everybody has seen what happens in case bones do not get calcified. They are actually quite soft, and that softness, flexibility of the bone is really due to the collagen fibers, that those are protein fibers, right? So without calcification, they are really soft. Okay, so inorganic components. Most important thing to relate to bones. If you hear hydroxyapatite, you think bone. Okay, so in the test, if I say something like hydroxyapatite, you're going to think bone. Where else are you going to find hydroxyapatite in the body? Nowhere else. It's just in the bone. All right, so that's an easy one. One thing you have to remember. Okay, hydroxyapatite is bone. And now, what is going to make this hydroxyapatite? Basically, you have these calcium phosphate crystals that are inside the collagen fibers and around the collagen fibers. Those are very, very important to give the hardness of the bone. Okay, so as we compared before, these hydroxyapatite minerals, they are like the cement when you are trying to build a building or some structure, right? If you use only this inorganic cement, if you hit the structure with a hammer, it's going to crumble. It's very fragile in that sense. Now, if you put steel beams through that structure, then it's going to be a lot more resistant, right? So basically, the collagen fibers are those steel beams, and hydroxyapatite is the cement or the mortar that keeps the structure together. Okay. So this is responsible for hardness. It is also resistance, responsible for the resistance to compression. Okay. When you compare it to the function of collagen fibers, those are very good at resisting tension. Okay, so this is resisting compression, that one is mainly for resisting tension. Okay. So, dense connective tissue in the bone is only about 2% of cells by mass. So, when you look at the matrix of bones, this is made of about 25% collagen fibers, 25% water, and 50% mineral salts. Okay, so it's a lot more inorganic material than you have of organic material. Okay, and then if we say hydroxyapatite, you think bone. Okay. Okay, now, yeah, basically combination of calcium crystals. And you do have other minerals that can also accumulate in the bone. And actually, a bone can be a kind of like a sponge or sucking up some type of toxic chemicals that can get to the body. Like, for example, lead. Have you heard of lead poisoning? Yeah, everybody heard of lead poisoning? What does it do? Besides poisoning you. Where is the main organ that gets affected by lead poisoning? The brain, right? Very big problem, especially when children get exposed to lead poisoning. Now, once the lead is in the circulation, the bone will tend to absorb the lead poisoning and lock it into the crystals. That's a double problem, because even if you stop the exposure, okay, of that child to the environment that contains lead, the bones already have this internal exposure, and the child is going to keep on being exposed through a long time until, you know, somehow all this lead, the bone is going to reshape and reconstitute, and this lead is going to get rid of. Now, imagine that the higher concentration or the higher exposure is really a bigger problem, because you're going to have a lot more internal accumulation of lead, right? So this tends to be a big problem with the accumulation and retainment of lead in the bones. All right. Okay. Now, bone development. This is a part that drove me a bit insane, and I'm so glad I'm not the only one who's really insane. You know, we had about 15 people in this symposium in Washington, and everybody was complaining about the description of bone development in every single textbook out there. I'm like, oh, thank goodness! I thought I was just speaking, you know. But no, it's real. The problem is real. So let's make sure you understand what is happening here, okay? Because it's, at the same time that it is a problem, it's actually a very important conceptual topic that you absolutely have to know. Right? So I try to digest as much as possible here and put it as in the simplest way possible to be understandable. Right? So let's take a deep breath and let's go through this. All right. So basically, when you have bone development, you're going to have ossification, right? It's also called osteogenesis. And this ossification process, connection is low again. Okay. This ossification process is happening in uterus, right? And begins around 8 weeks of pregnancy, about 2 months, 8 weeks of pregnancy. And it happens also after the child is born until early adulthood or so. Now, the remodeling of bone doesn't stop. It happens throughout life. Well, I'll say stops after, you know, person dies, but yeah, doesn't stop. Now, up to about 8 weeks, you're going to have fibrous membranes that are going to allow some bone development in specific bones, and you're also going to have hyaline cartilage development of bones. Okay. Now, hyaline cartilage development starts a little bit earlier than the fibrous membrane bone development, but is not too far apart. Maybe hyaline cartilage may start at 6 weeks after of pregnancy, and fibrous membranes starts at about 8 weeks. So they're like just hyaline cartilage a little bit before the fibrous membrane development. Okay, now when you look at the fetal skeleton and you see this bone development, don't think that the cartilage just transforms itself into bone. That's not what happens. It gets replaced by bone tissue. Okay, the chondrocytes do not magically decide to become something else. Okay, they die and then they get substituted by mesenchymal stem cells that then become bone cells. All right, so there's no magic switching of cell types in here. Okay. So these two types of bone development, endochondral ossification, that's the one that needs the cartilage, as we see here, chondral, that is word that goes with the cartilage, right? And then the other type is intramembranous ossification. It means in the membrane. Intra means inside, and then membranous, of course, is inside a membrane. Then you go say, what membrane? Well, we're going to see that next. So let's look here. What is happening with these two types of bone development? Okay. So here, when you have here your little fetus that is about 5 to 6 weeks in utero, right, in development, you have these models or little shapes that they're just serving us as a scaffolding or some type of, not scaffolding, there aren't other words, but just some type of, well, model is really the right word, that is almost looking like a bone, but it's not a bone. Okay, so this is just cartilage. And those that are going to form most of the bones of the body, except for the head and clavicle. Okay, so those are really all over the body, They're just starting to form this hyaline cartilage type of shape that looks like bone. Okay, so here, of course, this is the arm of the fetus, and you know that this shape here is going to become the humerus, and then here you have the radius, the ulna, and then carpals and the fingers. Okay, so now let's see what happens here. This is the part that drove everybody crazy. Okay, so endochondral ossification. So first thing that happens, you have your cartilage, right? How does cartilage receive nutrients? How is it that you have these cells, these chondroblasts and chondrocytes inside of the cartilage? How is it that they survive?
Connective tissue underneath it?
No, how they getting fed? Do you see blood vessels in cartilage?
No.
Okay, how many people say no? How many people say yes? Ah, God, no, I cannot vote twice. Okay. No, this is one of the hallmarks of cartilaginous tissue. There are no blood vessels. Cartilage is avascular, right? So the cartilage here, you don't see blood vessels there. So how is it that these cells are getting their nourishment? Yeah. Diffusion. Yes. Let's give her a round of applause. It is diffusion. Now, think about it. As this model of cartilage is growing, when it's tiny, you get diffusion. Cells inside are happy. They get the nutrients, they get rid of the waste products. This thing starts growing. Now we have a problem because diffusion to the center cells, it's not efficient. So the center cells is kind of start getting very unhappy, okay? Because they're not getting nutrients. So this is the most important point in this transformation from, or this shifting from hyaline cartilage to bone tissue. Okay, so keep that in mind. As the tissue is growing, this thing is avascular, so cells in the middle are not going to be happy. Okay, let's see what happened here. So this is from, I believe this is from your book or from another source. Look just like your book. Okay, So here you have the model of cartilage first, right? So as we're going to see, as I have it broken down by slides. So the first, the chondrocytes, right? These chondrocytes in the center, as this structure is growing, these chondrocytes start to become unhappy. And it makes sense that they are in the center becoming unhappy, because the ones that are close to the edges, they are getting plenty of nutrients by diffusion. The ones in the center, they are unhappy because the other guys already got the nutrients before the nutrients could get to them. So they are kind of like really stressed out. When they have lower level of nutrients, then they start to express some protein, and they start to deposit matrix around themselves that it starts to be calcifying. So this starts to become calcified cartilage. Okay, so it's still cartilage, it's not bone. Okay. Now, after this model is a certain size, then you're going to have ossification of the outside, okay, outside of the bone. And this is called the collar, bone collar. Okay. Now, the cells, these chondrocytes inside this shaft of the bone, they are even more upset, because not only they didn't have enough stuff coming from diffusion, now they have a barrier all around this bone. This is not only on the sides, okay? This is a collar, goes all around the bone. Now they're even more unhappy because they're getting further blockage of nutrients, the stuff that is getting to them just a little at a time. Now they have this wall that is totally going to block this diffusion of nutrients, okay? So guess what's going to happen to them? Guess? They die. That's easy. Okay. So now, before we get into the other parts, let's go to each of these processes here. So here, the first thing, endochondrial ossification happens to all bones under the base of the head, okay? And except the clavicles, those are also intramembranous ossification, but no, not the head, not the clavicles. Everything else happens by endochondrial ossification, okay, in uterus. Begins around 2 months of development. Remember, it's formed by hyaline cartilage, and then some parts of this bone keep on being hyaline cartilage. No wonder that your joints are made of hyaline cartilage, right? Okay. So at first, when you have these central bones that are starting to die, okay, so at first you have the formation of these walls, right? There are this bone collar that is forming not only in the sides but all around the bone, and then you get these mesenchymal stem cells that are also present inside of the bone, okay, and those when the chondrocytes start to put some hard mineralization in the matrix, they're also activating the stem cells or the mesenchymal stem cells to become osteoblasts. Remember, osteoblasts are the cells that are giving origin to the bone tissue. Okay, so this is what is happening at first. So at the same time, you also get this deposition of the bone around the diaphysis, right? So that's called the collar, the bone collar, right? Not the collarbone, that's something else, right? So this is the bone collar. And what else is important here? So this is the part that is important to know. The chondrocytes are enlarging. That means they become atrophied. They're getting big, right? They're enlarging because they're upset. They're not getting nutrients. So they have lack of nutrients, they're getting bigger, and at the time they start to produce this enzyme. If you want to know the name of the enzyme, is alkaline phosphatase, okay? And that is going to promote the calcification of the matrix, or the ground substance that makes the matrix, okay? So this all is happening here. Why? Because this cartilage reached a certain size that is causing all this transformation to happen. Okay, so it's not by magic. It's because of first lack of diffusion of the nutrients, and then the cells start to either upregulate certain genes or downregulate some other genes or activate stem cells that are already inside there. So this process is happening all at the same time, and once you have deposition of minerals from the chondrocytes, you call that area here your primary ossification center. Okay, so you see it over there. It's like some hardness is starting to appear inside after this bone color developed all around the bone. Okay. So now what's going to happen here? This calcified matrix that is inside that primary ossification site is also going to make it impossible for nutrients to diffuse to the chondrocytes. So the chondrocytes that were already unhappy, now they're just going to die. Okay, I guess, they totally get unhappy. That's it, death. Okay, so no more nutrients for them. Everything got calcified around them. They just die. Now, the center of that thing is really far away from blood vessels that are outside. Remember, the outside of the bone, the periosteum has blood vessels, right? But the center does not have blood vessels. So when these cells die and then you have this calcification going on, at that time you have this blood vessel that gets inside of the bone, that invades the inside of the bone, right, by the nutrient foramen. Did I write it here? If not, here must be in the next slide. Or make your own notes. That's the nutrient foramen of the bone. Okay, it's a hole in the bone in which the main blood vessel will go inside of the bone. So now, once you have these blood vessels that go inside this little hole that was made by dying cells, right? This blood vessel is also bringing more mesenchymal stem cells, okay? And those stem cells here, they are going to differentiate into osteoblasts. That means they are going to start making new bone inside. Once you start making the new bone, you are going to make, at first, spongy bone, because this is how the progress of bone formation works. Okay, so at first you're going to make spongy bone. You're going to have a lot of osteoblasts in there. But then at the same time, you're also going to have cells that are that are getting in there and differentiating into osteoclasts. Remember, they are not from the same cell lineage. Osteoclasts are the cells that are going to destroy bone tissue, and those are derived from the myeloid lineage, the white blood cells lineage, right? So it's not the same lineage as your osteoblasts. Okay? So these osteoclasts also get in there, and then they start to get rid of all the junk that was left behind by the cartilage. So cartilage is going to be gone once osteoclasts and also, what's the name of those Pac-Man cell? Macrophages, right? Macrophages get there and start eating up all this debris and clearing up the center of dead cells and debris that was left there. And this is how you start to get this empty space that is the medullary canal, or the marrow part of the bone. Okay, so it's empty in there. Why? Because these cleaning up cells went there and cleaned up stuff. Now, this is happening. Look at it. It's not a coincidence that is happening in this region over here. Okay? You look where you have your bone color right there. Remember, it's not only on the sides. Think 3D. And this is one thing I was asking McGraw-Hill to develop. Okay, so this 3D image of this bone color going all around, right? Now, do you see any part of this bone in which you do not have this bone color? Everybody awake here? Yes? So just look at the picture. What do you call the ends? It starts with E? Epiphysis. Epiphysis. I know these words are so annoying. But you have to remember them. Why? It's not that I like them, but I have to ask you about them. Okay? Is it going to be in the test? Yes. Oh, that's my other deal with you. Wait, let me stop here. Wait. So coming back here, and I mentioned that because I was thinking about epiphysis at the end of the bone, and then you have the diaphysis in the middle, and then you have those metaphyses, and those are also called epiphyseal plates. Don't get those confused. I've seen tons of multiple choice questions that love to confuse the students on those names. Okay? Epiphysis on the edges. Now, epiphyseal plate is the same thing as metaphysis. These metaphyses are just before the epiphysis and between the diaphysis and the epiphysis. So the metaphysis, you have one here and you have one there on the long bone. Okay? So this metaphysis is where you have hyaline cartilage in growing bones, and in the hyaline cartilage you are going to have chondrocytes that are capable of cell division. That means the bones can grow. Thank goodness. We are not the same size, the same height now as we were when we were just born. So bones do grow after birth. I hope nobody's surprised by that, right? And the bone tissue itself is not going to grow because remember those osteocytes are stuck in their little lacuna and they can't really be dividing. They don't divide, right? But here, when you have this epiphyseal plate and you have the cartilage there, those can grow. Now, which direction do you think this thing is going to grow? Do you think it's going to grow like this way, or you think it's going to grow that way? Well, which way? It actually grows more like this way here down than up, but it basically grows both way. But then, yeah, this part of the bone here tends to grow this in this direction here. So then next time you look at the bone, you're going to have this epiphyseal plate that is like up here, and then this whole thing is going to be diaphysis, and then the epiphyseal plate down there. Okay? All right, so here you have your epiphyseal plate that is growing, and then here at the epiphysis, you have more of this hyaline cartilage that is over there, but then depending again on the size of the bone, it's going to start having the same problem as you had in the middle here, because although it doesn't have the color going around, it's going to reach a critical size that diffusion is going to make this center here very upset, right? So now let's see what happens here. When that happens, you're going to have these secondary ossification sites, okay, both in the proximal and distal epiphysis. Okay, so secondary ossification sites are going to start happening, and then the same process is happening as it happened here before, with the difference that the spongy bone here is not going to be destroyed by those osteoclasts. So the epiphyses are going to maintain the spongy bone structure, okay, after this ossification site develops. Right, so you're not going to see this marrow cavity at the epiphysis. It doesn't mean it doesn't have bone marrow. It does, right? The bone marrow is in the spaces between the trabecula over there. Okay? So that's about your secondary ossification center. And also keep in mind that the edges here at your epiphysis, you're going to keep that layer of hyaline cartilage, because at the end of the bones, that's usually where you're going to have connection with other bones, and you're going to need joints, right? You're going to need articulation to happen there. So you have your articular cartilage that are going to be deposited here. It's going to be kept at the ends of your bones. Okay. So here's a little summary slide of your endochondrial ossification. So endochondrial means inside of cartilage. So this is not a direct way of making bone. First you have to make your little shape with the cartilage, and then after that you start making the bone. So this is kind of like a secondary way of bone tissue development. It's not a direct way of just making the bone. Okay? So this is another difference between endochondral and the intramembranous ossification type of thing. Oh, another question. Okay. All right, so here we go. Which characteristic of cartilage enhances its job as the precursor to endochondral bone? Gotta think about that. Let's see what happens to this answer. And accommodate mitosis. Yeah, see, I don't remember when I put this question there, but I think that's the correct answer. Yes, cartilage can accommodate mitosis. All right, so this was the correct answer for here. Now, if you didn't even know the answer to this, just go by logic. Can cartilage decay easily? I hope not. We have joints that we have to use throughout life, right? So hopefully not. Is cartilage a weak tissue? Not really. I mean, if you compare to bone, it's weaker than bone, but it's not a weak tissue, right? If you're running around, you want your cartilage to be nice and strong and consistent, right? Cartilage is retained as part of the skeletal system. Is that a reason for a precursor of endocrine? That doesn't make sense, although it's a statement that is not necessarily wrong, right? So really, the most obvious answer here is cartilage can accommodate mitosis. The bone itself, the bone tissue, is not going to undergo mitosis. Okay, so now we go to this other guy, intramembranous ossification. That tells you it's happening inside of membranes. You say, what membranes? Well, the membrane that is right over there at the head of this fetus, right? So first you have this membrane. It is fibrous connective tissue, right? Now, what happens in that tissue is that you're going to also have these mesenchymal stem cells in the fibrous connective tissue. And when those mesenchymal stem cells are getting together in this fibrous mesh, okay, so now you think about, anybody go shopping here, like supermarket? You buy onions, you make your own food? Okay, so if you buy onions, you know what the mesh of the onion bag looks like? Yeah, so even if you don't buy the onions, go to the supermarket and look at the mesh. So that's the membrane that this thing is looking like, right? So this membrane here, at certain point around 2 months of gestation, you have these stem cells that get stuck in the mesh. So when they get stuck in that mesh, is that mesh cartilage? No, no. The mesh is not cartilage, it's a membrane. This is why this thing is called intramembranous. It's not intercartilaginous. Okay? It's intramembranous. So osteocytes get in there, and they get close to each other inside of this mesh, and then they start to differentiate and make bone. So this is a direct formation of bone tissue. Another difference between this and the cartilage stuff. You don't worry about making cartilage here. You just go straight from cells in the membrane to bone tissue. Okay, so this is one main difference in these two types of ossification. So now what's going to happen here? You have this mesh, you have these stem cells, mesenchymal cells is another name for stem cells, right? You have these stem cells, they sit in the mesh and they differentiate into osteoblasts. And what are the osteoblasts going to do? Make bone tissue. Everybody got that? Good. Do you have questions about that? No? No? Everybody know? Good? All right. So that becomes this ossification center right there, straight on the membrane. Okay. Now, what are the bones that are going to show up based on this developmental process? You're going to have the frontal bone. So we talk about the head up, right? You have the frontal bone, parietal bones, occipital bone, temporal bone, and also clavicle bones, right? Clavicles, parts of the clavicles develop like this. Okay. So what's the process of this thing going on, right? So here you have your mesh, your onion bag mesh, okay? And then those cells get together in the mesh. Is it only one ossification center, or what do you think? It can be several? It's several, it's not just one, because you have to make a whole bone out of this thing. If you're going to start in only one ossification center, it's going to take a very long time. So this thing is happening in several places of that particular bone, okay? So you have your ossification center, and just because these mesenchymal stem cells, they got there, they started to differentiate into osteoblasts. Now the osteoblast is going to start to secrete the matrix that is going to start calcifying around them, right? It's going to start secreting the bone matrix. So what do you call the uncalcified bone matrix stuff? Osteoid. Just follow the jumping ball, right? Osteoid, okay. Before it gets calcification. All right. Then the osteoid gets calcification, right? So this is now called the bone matrix. It's not the osteoid anymore. Now it gets those hydroxyapatite crystals, right? Gets calcified here. And the bone, the bone cell that was the osteoblast, that is secreting all this matrix here. Remember, it starts secreting matrix all around, and then it gets stuck because this is getting calcified, and then it can't go anywhere else. And it's like, oops, I can't be so active anymore because I don't have anywhere to work. I'm kind of stuck in my own little lacuna, right? So this guy becomes an osteocyte. Same thing that happened with other bone tissue formation, right? So once this is happening, you also have osteoblasts that are around the center of ossification, and that is going to give rise to the periosteum, right? That's around the bone. Okay. So now you have your osteocytes there. Okay. And let me see what's important here. They become osteocytes. All right. So when this structure starts to grow, it is going to start to become this woven bone tissue at first. Woven bone is just the predecessor, is the type of bone that just comes before the spongy bone. So this is like initial spongy bone formation. It's the same kind of tissue, same kind of thing, okay? So first you have this woven type of bone, then you form in the center, and then as this woven bone matures, it develops into those trabecula, and it's the same thing as we have with the spongy bone formation. So the outer layer here is going to form that tough membrane, the periosteum around here. So stem cells forming the periosteum, and then the center of these bones. And remember, bone is always very vascular. It's a lot of blood vessels in the bone, right? So then you have your spongy bone formation in the center. And as this spongy bone formation matures and you have your periosteum that forms on the side, the space that is just before the periosteum, it starts to develop into a compact bone. So this is how you get the sandwich type of formation. You have the development here of this compact bone, and then the center continues to be spongy bone. And then close to the other side, close to the other periosteum, you have more compact bone development on both sides. And then remember that this space in between this trabecula, that is filled up with bone marrow, right? So mainly in flat bones, you're going to have red bone marrow. In the long bones, you can have red or yellow. As you get older, you get more of the yellow one that is actually fat, right? But in the flat bones, you have red bone marrow. So here a little summary for you to write down the stages, the 4 stages of development of spongy bone in your intramembranous ossification process. Okay. So here is another illustration of what kind of membrane can give rise to this type of tissue, of bone development, right? So if you look here, you can see that the dermis side, right? Dermis, not the epidermis, right? But then you have epidermis, connective tissue, and then you have the dermis side can give rise to a spongy bone. Because remember what's the structure that you find in the dermis? You have some connective tissue, you have layers of connective tissue over there. That was in the last test, I think. So those membranes can give rise also to this intramembranous bone formation. Okay. Now I just hope that nobody asks me a question that always pops up. Okay, so here is another little slide exemplifying exactly the stages that are happening for this intramembranous ossification. And here is another question. Hey, I tell you, full of questions today. The principal component of bone that contributes to its hardness. I do hope everybody gets this one correct. Come to my office hours. Okay. It is hydroxyapatite. All right. Hardness of the bone, that's the concrete, that's the mortar, is not the steel rods. Steel rods is collagen, right? Hydroxyapatite is this hard stuff that goes in the bone. Do you know how you can dissolve hydroxyapatite from bones? Calcium crystals? Do the experiment at home. It's really, really fun. You get a chicken bone, you put it in a cup with vinegar. The more concentrated the vinegar, the better. You wait a few days. I don't remember if it's days or weeks. Well, the stuff is not going to go bad because vinegar is kind of a preservative. Okay, so you just leave it there, and once every few days or so, you test the bone to see if it is hard enough or not. The acid in the vinegar is going to dissolve the hydroxyapatite. Okay, you don't need to use hydrochloric acid. Don't use that at home. Just use vinegar. It's going to work, I promise you. Okay, so the acid is going to dissolve the hydroxyapatite, and then at one point, all the hydroxyapatite is going to be out. These calcium crystals are going to be out of the bone. You can pick up a bone that's going to bend just like a rubber band. It's really cool. It looks like a bone because what gives the shape of the bone is really the architecture of the collagen fibers. But then you bend it, and it's not hard. It's kind of creepy, actually. But do the experiment. It's fun. And then you're going to remember, acid is dissolving hydroxyapatite, right? Okay. All right, so bone dynamics. The bones, the constant kind of got cut up here. They're always going through change. It's constantly being reshaped, okay? And when you actually use your bones, walking, exercising, running, you are causing this effect that is called piezoelectric effect. Okay, piezo for stepping, electric for electrical current. So when you think stepping, electrical current, electrical stepping current. Okay, so think that. What is happening to your bones? Well, we know the bone is not a straight stick. It has a little bit of a curvature. So when you step on the bone, a part of the bone is going to get a little bit of tension more than the other side of the bone. So that is going to trigger remodeling of the bone to create new bone at the site that you actually need more support. And here at the site that you don't need so much support, you can do a bit of a bone reshaping, dissolving to shift the weight to the other side of the bone. And what happens in the middle? Like if you have more strength here than there, the middle, nothing is really happening in the middle, okay? So that's why you can actually afford to have a hole in the middle of the long bones, okay? Now, this reshaping, control of remodeling, due to mechanical stress it has a name. It's called Wolff's Law. Okay, so Wolff's Law is what says that is what dictates the remodeling of the bone based in response or the demand of the bone. And also keep in mind that you're only going to be building bone tissue if you're actually using your bone tissue, right? It takes some months of continuous or periodic but constant use of your bones, exercising basically, to build new bone, right? But then if you're not going to use the bone, in other words, if you don't keep on exercising, it also takes a few months to get rid of that bone tissue that was built. That's why continuous exercise throughout life is important for maintaining healthy bones. Okay? So keep that in mind, because the idea of keeping healthy bones is that if you don't use them, you lose them. Same thing in comparison when you get to the muscle tissue. If you're using your muscles, if you're building up, you're going to the gym, you're going to have nice muscle mass. But then if you stop going to the gym, you know what happens to muscle mass? It kind of goes away, right? It disappears, atrophies, right? Now, easiest thing to remember Wolff's Law. If a wolf is running after you, you have to keep on running and remodeling your bones, right? I don't know if that helps you. Okay, so exercise increases bone density. So this is a person who is very sedentary, and this is a person who exercises. You're going to increase bone density, bone mass, by exercising. All right. So when you talk about bone formation, bone forms in basically 4 types of situation. Of course, when you're developing in uterus, it's good to have bone formation. Then during growth until adolescence or young adulthood. And bone remodeling happens throughout life. It doesn't stop. And then you have fracture healing. That's a very good time to have your bone remodeling and bone formation process going on. Okay. Now, things that affect bone formation and maintenance: nutrition and hormones. Not just hormones, not just nutrition. You gotta have a combination of both, okay? So here, you need vitamins along with calcium-rich foods, okay, preferentially. Personally speaking, I don't like supplements. I kind of like, if I have to take a supplement, like, yuck. So get it from your foods. Now, if you don't have the proper vitamins and calcium, you can get rickets, which is a failure of calcification of the bones. If it happens during a growth stage, then the bones don't get quite calcified. Now you think chicken bone in vinegar, right? So in this case, I never got the calcification in the first place. So the bones throughout the body of these children, they're going to be kind of soft. And then, of course, you're going to see a more pronounced effect on the legs, because if you think about arm bones, they're not bearing that much weight. The legs are bearing all the weight, right, of the rest of the body. So you're going to see this type of misshaped bones basically on the legs of the children that are not having proper vitamins and or calcium in the diet. And this is a very extreme case of rickets here, poor kid. Okay. So what can lead to that? If you have lack of vitamin D, all right, so if you don't go out too much in the sun, but remember I mentioned before that in this country all the milk is fortified with vitamin D, right, which is derived from cholesterol, from steroids. So not only vitamin D, but also vitamin C. But when you look at cause of rickets, is basically a lack of vitamin D. And vitamin D helps with absorption of calcium from the intestines. So even if these children are eating calcium-rich foods, but without vitamin D, they're not going to be able to absorb the calcium from the foods. Okay, foods that contain calcium. Oh, surprise, surprise! Lots of vegetables. Yay! Eat your vegetables. Like, pick your favorites. I like avocado. Gooseberry, squash, close to Thanksgiving now, right? Oh, still have Halloween horrors. Anyway, eat your vegetables. I wonder if I give vegetables out for Halloween instead of Halloween candy. If my house is going to be very popular. No. Okay. Now, if you don't get vitamin C, then you're going to have another problem. You're going to get scurvy, pyrite disease problem. Okay? So that was very typical of Arctic regions. They don't have a lot of stuff with vitamin C, like in the poles, in the North Pole, Arctic regions or South Pole, where they're gonna plant their oranges. Yeah, problem. Yeah, yeah. The scurvy came from a word that means disgusting. So these poor people are having decay of the teeth, of this connective tissue that is putting the teeth together. And the blood vessels don't have a lot of resistance, so they will break and they have bruises, and it's not fun. So mainly, eat me, you scurvy dogs. I just thought this was a very cool picture I stole from another professor. Cool. So now, other than your diet for strong bones, hormones are very influential in bone growth. First thing, when you're growing children, the most influential hormone for bone growth is growth factor. Okay, so growth hormone is going to stimulate growth of bone. And where is it that bone is going to grow? In the long bones? Metaphysis is also called epiphyseal plate. That's the only place that allows for long bones to grow, right? And you have other forms of growth too, but that one is I emphasized before. Okay. Hormones like thyroxine, right? This is from the thyroid gland. Okay. Calcitonin, iodine, important hormones. Those are going to increase protein synthesis and rates of growth. Now, let me see. Now, this hormone based on the thyroid gland is also important for mental brain function, okay, mental processes. Okay. Now, when you don't have the thyroid gland that works properly, you can have a disease that is called hypothyroidism, and that is associated or was first associated with cretinism or not very good mental function. We don't see much of that now. I'm running out of time here. So I'm going to stop here. The metaphysis, this slide that shows the metaphysis, that's the site of your long bone growth.